Greetings. My name is Basar Bulut. I work as a tunnel ventilation and fire life safety specialist in COWI, and today my presentation will be about the emergency egress doors in road tunnels and their possible optimization. Firstly, I would like to go through a previous study that we finalized last year, which forms the basis for today's presentation as well, and forms the motivation for this study. Then I will briefly describe the model alongside with the assumptions, and then we'll directly jump into the results. Whenever we design the metro tunnels and use the cross passages to serve as exit, as per NFPA 130, these cross passages shall be not further than 244 meters. Although NFPA 130 later on added the fire risk approach and the engineering analysis to possibly increase this value, out of curiosity, we just wanted to analyze the possible impact of each variable on the evacuation time. The train in consideration, if it has 4 rolling stocks, the cross passages shall not exceed, the distance between the cross passages shall not exceed 244 meters. The same stands still for a train with 6 and even 8 rolling stocks. Although the number of passengers vary, these requirements stand still. So out of curiosity, we performed more than 1,000 evacuation analysis to understand the impact of each variable on the evacuation time. And what we found is actually the number of passengers that the train has almost 4 times more effective than the distance between the cross passages as expected. The more the passengers, the more evacuation time it will take. But more importantly, the width of the walkway is almost as effective as the distance between the cross passages, which yields that if we can accommodate a relatively larger, wider walkway width, it may be possible to maintain the same evacuation time while exceeding the distance between the cross passages. Since we have already these more than 1,000 analysis results, we also conducted a regression analysis to come up with this formula, which is quite applicable within a range of passengers between 800 to 1,600, between the cross passages that are separated between 240 to 500 meters, and the walkway widths not exceeding 85 centimeters. Of course, if we go beyond this margin, I cannot guarantee the effectiveness of this evacuation time, although it varies plus minus 2 minutes variations as expected. So the motivation for today's study is, can we apply this similar approach for a road tunnel and come up with the same or similar thing or not? So we wanted to analyze the effects of each variable on the evacuation time and their importance, and then try to formulate an evacuation time and analyze possible adjustments to the exit distances along a road tunnel. For this, we considered a road tunnel, the length between the portal is considered to be 1.2 kilometers, and the lane width is considered as 3.7 meters. We considered 5 different variables, which are the lanes. That can be a 2-lane, 3-lane, or 4-lane tunnel, and with various distances between the cross passages, various walkway widths, various widths of the exit doors that are leading to an exit, and finally the number of motorists inside the incident tunnel. Here is a screenshot for a 2-lane tunnel that we modeled in Pathfinder. I'm sorry I couldn't fit the whole tunnel as it was very small screenshot, so I hope this explains it more clearly. The entrance portal, the exit portal, and separate cross passages for each model is modeled in Pathfinder. What we considered here as per the occupant sources is they are aligned such that they are sited at, they are placed at each side of the vehicles to provide at least a bit realistic case. And to determine the number of motorists, we refer to RVS standard, where passenger vehicles can be considered as 1.4 motorists per vehicle. For HGV, 1 motorist per vehicle, and for buses, 40 motorists per vehicle are considered. So on the right-hand side, you can see the table that we filled this 2-lane tunnel with this number of vehicles, summing up to almost about 1,900 passengers, motorists, I'm sorry. And for 3-lane tunnel, it is almost 2,400 motorists spread throughout the tunnel. And for the 4-lane tunnel, we come up to almost 3,000 number of motorists. So the idea is that we take 10% of it. So we took a margin to vary between 1,750 to 3,250 motorists to vary for each scenario randomly. We also assume 2 different traffic conditions, which is the first one is the highly congested, almost stop traffic condition. So all of the cross passages alongside with the entry and exit portals are treated as exit points. The second traffic condition is the flowing traffic condition, where we assume that there's an emergency right at the exit portal. So for this traffic condition, the exit portal cannot be used by the passengers. The walking speed for the motorists is assumed to be constant and shall not exceed 37.7 meters per minute, which can be arguable upon for sure, but I don't think it would be more critical, as the queuing takes a long time rather than the walking distance. And we also provide space between the vehicles longitudinally to provide additional alternative route for the passengers to choose. So in order to finalize for one case, we have 3 number of lanes. We have 5 different distances between the cross passages, 3 different walkway widths, and 3 different exit door widths, summing up to 135 simulations just for one case. So jumping into the results, firstly, we considered the highly congested traffic, and we simulated 540 different scenarios and come up with the results, and then we tabulated these and introduced them to a machine learning algorithm where we analyzed the impact of each variable on the evacuation time to find that actually the distance between the cross passages is almost 66% more effect on the evacuation time. But here we introduced the number of lanes, but the more the number of lanes means the more the number of vehicles, which leads to more the motorists. So later on, we resimulated and rerun this remodeled the machine learning algorithm, excluding the number of lanes. And as expected, it accommodated to the number of motorists impact on the variable. What's surprising here to us is that the walkway width has almost no effect at all and can be considered as negligible, while the distance between cross passages is roughly 2.5 times more effective than the number of motorists, which is exactly the opposite of our previous study. For this 540 simulations, we also run a linear regression analysis with an R-square value of 96.5%, which is good actually, and we come up with this formula that can be used to determine if in the early phases of the design as well. And you can see in the residuals that it varies between plus 100 seconds to minus 108 seconds, which is relatively 1.5 minutes to minus 3 minutes, which can be considered okay, I presume. For the flowing traffic, we did the same thing, and we come up with the similar results. And here you can see the impact of the number of lanes when it is introduced in the model, sums up to 68% impact for the cross-passage distances. But later on, as we did in the previous case as well, we excluded it to accommodate for the number of motorists impact in terms of variable. So it is somewhat similar to the highly congested traffic condition as well. And for this flowing traffic, we found exactly the similar R-square value, which is 96.5%. But this time the residuals vary between plus 160 seconds to minus 220 seconds, which is relatively larger than what we found previously. Just to show how the distribution of the passengers, how their choice in terms of exits were in the simulations. Here is a show for here are the graphs for the 4-lane tunnels with 7 cross passages. On the left hand side is where the highly congested traffic condition is. The exit portal is usable. But for the flowing traffic condition, when it was kept not to be usable in the simulation, as can be seen, the 7th cross passage became highly congested, and a similar thing for the 9 cross passages situation for a 4-lane tunnel as well. So coming to the conclusion, we can say that actually the cross passages distances is the most effective variable in the road tunnels, which is quite the opposite of what we come up with in our previous study. And it is 2.5 times more effective than the number of motorists that are considered in the simulations. However, the effect of the door width on the evacuation time, when we compare it with the distance between the cross passages, is found to vary between 9 to 13% of that. It is not that effective, but it is still possible to say that if we can increase the door width relatively, it's still possible to achieve the same evacuation time, or even the shortened evacuation time, even with the increased distances between cross passages. And finally, the width of the walkway is surprisingly found to be almost negligible. Of course, while we have this data available, which consists of 1,080 in total simulations, we are still running this in other machine learning methods to increase the R-square value, for possible increase in R-square value, to find a more optimized condition, to more optimized equation as well. For this Lossa model, we were able to obtain 97%. However, using a ridge model, it's slightly lowered. We are not satisfied with this R-square value that we come up with. But we also use the random forest regressor model, which gives promising results with exceeding 98% values. And if we consider the residuals here, they seem to vary between plus 1 minute and minus 1.2 minutes, which is more promising than the linear regression analysis. So the idea here is to make benefit of these tabulated values, try to extend the number of the simulations, and come up with a pickle file in Python, and then implement it into the Dynamo module for BIM analysis to determine the life safety and means of egress analysis for the road tunnels. And we have an ongoing project as well, which is related to the tunnel ventilation simulations in road tunnels. And in the future, we are aiming to combine these two to propose a performance-based modeling for the road tunnels, which later on can be used as a digitalized tool to implement in the BIM. thank you for listening to the presentation, and I hope you like it. I will be available for any questions that you have, and thank you for your time.
Okay, hello, can you hear me?
Yes, I can hear you. Hello.
Great. Thank you for joining us.
Good afternoon, good evening, wherever you are in the world.
Yeah, we hear you well. Thank you for joining. We'll see if we have any questions here. Checking online, and we'll look around here. Yeah, one comment. I noted here while we were listening that there's some work that some of our developers doing on a new scenarios feature in Pathfinder that will allow you to change parameters at the parameter level and could generate a whole bunch of different variations of your case in the same file, but moving things around, changing parameters, enabling, disabling. I said this would be a really good test case for that new scenarios feature, since you made like 135 scenarios essentially, or models. It'd be nice to see how much of that you can keep in, you know, maybe one file or a couple of different geometry files with all the different parameters. So we'll probably be following up with you on that for, can we use your, use your cases for testing our scenarios feature?
That's very great news for me, actually, as it was a disaster to keep these files, my limited storage, and then, you know, transferring the files back and forth this many times. And I'm a bit of an old school guy, so I had to model everything on myself. So
yeah,
I'll be...
The other might be with the data processing utilities that we're coming out with too, to be able to get the results of those simulations and be able to compile or compare some of that through a Python library. I think could be useful. Let's see, I'm just looking around. Any other thoughts or questions? No, I'm not seeing any. So thank you very much for tuning in, and thank you for the presentation, and we'll talk to you soon.
Thank you very much.
All right, bye-bye.
Bye-bye.